Hey, what is up everyone? I am back with another review video, this time for ICS 33, and this one is quite a long video. I just finished editing and it took quite a while to not only record, but to edit as well. So I have a couple notes that I want to go over real quick before we start the video. I want to say that I did all this research, and I got a lot of it from Pattis's notes, but there was also a student a couple years back who condensed all of Pattis's notes into a more readable form, because Pattis goes very, very into depth, almost too in depth sometimes, and his notes are just ridiculously long. So I'm going to go ahead and link to both websites down in the description. And then I also wanted to say thanks to my friend Raymond for helping me out. He did notes for a couple of the chapters, because even though I used the condensed notes, there was still a lot of stuff to go over. So yeah, enjoy the video.
Alright, so let's hop right into this video, starting with week 1. So week 1 was just mainly review. We went over data types, iterators, comprehensions, function calls, lambdas, and classes. So first we're going to talk about directly iterating over values in a list versus using a range to iterate over indexes of values in a list. First we have the iterating of ranges. So an example is for I in range of the length of a list. This iterates over the index of values in the list starting from 0. And this is useful when changing the value of a list at a certain index. Next we have iterating over the actual objects in the list, which is for I in list, and this is useful for when you only need the value and not the index of a said value. Moving on, we have comprehensions. Now, comprehensions are compact ways to generate complicated lists, tuples, sets, etc. This allows you to compactly solve some, but not all problems. For example, you cannot mutate values in an existing data structure with a comprehension. So here's an example. We have fvar for var in iterable, and then if, and then there's a Boolean statement. So the Boolean statement at the end is optional, and these collect together in a list all of the fvar values, but only if pvar is true. Here's a more coding friendly examples. We have I squared for I in I range from 1 to 10, so that's an inclusive range, if I mod 2 is equivalent to 0. So this has the value of 4, 16, 36, 64, and 100, all compacted into a list. Continuing on with comprehensions, we have dictionary comprehensions. So this is the general form for dictionary comprehensions. We have our key, and then our value, and then for var in iterable, and then of course the optional boolean at the end. So here's an example. So we have k for the length of k, and then for the k value in this list 1, 2, 3, 4, 5. So this will go ahead and have a value of 4, then the length of 4, then 3, then the length of 3, which is 5, and then just that continuing down the list. Also, remember that dictionaries have no order, so they can appear in whatever order they please. Next, we have tuple comprehensions. So here's an example. We have I for I in ABC. Now, tuple comprehensions are interesting because they actually return generators, so you must use iteration to access the value. Next, we're going to talk about function calls. So anytime a reference to an object is followed by parentheses with some sort of arguments inside, it means to perform a function call on that object. So trying to call an integer or a string would raise an exception. And then here are some examples of function calls. So I'm going to go ahead and write a couple functions real quick. So we have a double function, which takes an int x, and it goes ahead and doubles that. So it returns 2 times x. Def triple, and we're going to give that an x as well. And we're going to go ahead and return 3 times x. And then we'll have def magnitude, which will also take x, and we'll return 10 times x. So that's all we'll need for this example. And then we'll go ahead and I'll show you if you set f equal to double, this sets f equal to the double function but does not construct a double object. So it will not return a value since we're not giving it anything. We're not calling the actual function. Now let's say we want to call multiple functions on one piece of data. So let's say for f in, and then we'll make a list, and in this list we'll put double, triple, and then we'll go ahead and put magnitude as well. Then we'll go ahead and just print f, and then we'll go ahead and give it the value of 5. So if we go ahead and run this code, Python run, you'll see that it will go ahead and go through all of these and then print 5. So 10 times 2 is, or sorry, 5 times 2 is 10, 5 times 3 is 15, and then 5 times 10 is 50. And then we can also do something similar with a dictionary. So let's go ahead and define a dictionary. We'll call it fs equals, and then let's get some curly brackets in here. We'll do the first key to be 2, and we'll go ahead and give it double as the value. So that'll be the double function, since that is the only namespace here. And then we'll have 3, which will be triple, and then we'll have 10, which will have the key of magnitude. And then we'll go ahead and print, let's say we want to print triple of 5 again. So we'll do fs, we'll give it 5, and then on that we will go ahead and call, fs, we'll give it 3, and then we'll call 5 here. So if we go ahead and print this again, we'll go ahead and add a new line somewhere in the middle here. You'll see that it indeed does print a triple of 5 down with the dictionary. Function calls can return references to function objects which are executed using the LEBG rule for binding. So L means to look for the name locally in a function. E means to look for the name in the enclosing function. G means to look for the name globally, module, and outside the functions. And then B looks for it in the built-ins module, which is always automatically imported when working in Python. So here is an interesting example with the old and ancient classes. In this example, we'll be going over the LEGB binding rules. So I'm just going to go ahead and write a function with a function inside of it. So we'll do bigger than, and it'll take a value v. And then in there, there'll be another function, and we'll just call it test, which takes a value x. And this inside function will return x greater than v, so it'll return a Boolean value. And then this outer one will go ahead and return test. So that's still there we go. All right, and so this is the only function we'll need for this example. So we'll go ahead and create a variable, call it old. We'll do bigger than, and then we'll give it the value of 60. And then we'll do the same thing with ancient. Ancient equals bigger than, and then we'll give it a bigger number, so we'll call it 90. And then I'm going to go ahead and print some calls on old and ancient. So if we do old 10, and then we do old of, let's say, 70, and then ancient 70, and then something bigger than 90, so we'll do ancient, and we'll do 100. So when we go ahead and print this, it'll do false, true, which I believe is correct, because if we go through and trace back the code, we have 60. So v is always going to be 60, so we're trying to see if the number we're giving it is bigger or smaller. So 10 is not bigger than 60, so that should return false. 70 is bigger than 60, so it should return true. Ancient is bigger than not bigger than 90, sorry. So this will go ahead and return false, and then 100 is bigger than 90. If we went ahead and changed this to 90, it should return false, because it is not bigger, it is equal to. And then to put it kind of into perspective, if we call bigger than, and then we give it the value 60, and then we call again 70, this is the same thing as printing old of 70. So this should return true, that Boolean statement, and which in fact it does. Now comparing functions and methods. Functions are usually called f of, and then parentheses, and then the given arguments. And then methods are usually called on objects like o, and then m, and then the parentheses with the parameters. So this is a special syntax to write a function call and brings up the fundamental equation of object-oriented programming. So here's the basic equation for this. So we have O of m, and then a function on that method, and then equals type of O, And then it's that same method call, but you're actually giving it the instance of the object. Type O returns a reference to the class object O is constructed from. .m means call the function m declared in that class. And then you pass O as the first argument to m when calling type. Now, recall when defining methods for classes we write. Def m, and then we give self as the first parameter. So that's essentially what we're doing on the right side of this equation. We're giving it the type, so we're giving it the class it actually is, and then we're handing it down the actual instance, which may have different stored variables inside. Continuing on, it's important to know that this is not true 100% of the time. If m is in the object's namespace, it would be called directly. Later in the quarter, we learn about class inheritance, and the inheritance hierarchy of a class provides other classes in which to look for m if it is not declared directly in O's class or type. Now, lambdas are used in expressions where we need a very, very simple function. We can use the keyword lambda followed by parameters, then a colon followed by a single expression that computes the value of lambda. So writing lambda xy colon x plus y is like writing a function that just returns the value of these variables added together. And here's a coding example of lambda. Alright, so continuing on to lambdas, I'm just going to show you a very simple example of a lambda. So something to note is that the parentheses around the lambda are not necessary. It's just something that Pattis said is a good practice, just to kind of, so you know exactly what is in the lambda. So here we have f, which is a function that just adds x and y. So if we go ahead and call f 1 and 3, and we go ahead and print this real quick, you'll see it'll give us the value 4 down in the console. And then if you recall the bigger than that we wrote earlier, we can actually rewrite it with a lambda, and it'll become much, much shorter. So if we do def bigger than, and we give it the value v, let's say, and then we can just go ahead and return a lambda here with x, and then x is greater than v, not a capital X, a lowercase x. And so if we go ahead and print bigger than, and we give it 60 and then 70 like we did in our last test last time, we go ahead and print it, it should return true, which it does. Moving on to classes, in specific, what we want to know about classes is the dictionary namespace for objects. Now, every object has a special variable named __ dict __ that stores all of its namespace bindings. Moving on to week 2, we mostly talked about regular expressions, matching language, and then extracting groups for matching. Regular expressions are patterns that we can create to search and or replace text in strings. The general rule of matching is that regular expressions match the most number of characters possible, and this is for greedy algorithms in specific. Now, the basic rules for matching, we have meta characters, which match any single character, except for, of course, special characters like \n, \tab, white space characters. So a pair of brackets and anything in the brackets matches any character specified in those brackets. When you have a caret in those brackets, it means that your string matches any character not specified in those brackets. And then when you have a dash in between the brackets, that means it matches one character specified in the range. So usually that's with numbers, integers, or like the alphabet. So from A to B, A to C, A to M, something like that. And then we have anchors that don't match a character, but they rather specify a behavior. So caret matches the beginning of a line. So if you have a caret at the beginning of a regular expression, the character immediately following it, when using it to compare to a string, say it's caret S, there has to be an S at the beginning of your string, otherwise it won't match. And then a $sign is like the exact same, but it's at the end. So the last character has to be whatever falls before the $sign. And so here is a chart of all the regular expressions that we should know. Generally, functions that use regular expressions use a regular expression pattern. So the compile function creates these patterns for us. This is the general form of compile. So you have compile, a pattern, and then your flags. We don't really need to worry about what the flags do in regards to this class, but just know that is an option, and this creates a pattern object. Now for matching objects, we have re.match, and as you see here, the first argument is a regular expression pattern, and then the second argument is a string. So note that this pattern matches the string AAAB because there's an A in the first slot, and then there's a B ending the string. But notice that this does not match the string BAAB. And here's kind of the breakdown of this pattern. So the caret at the front asserts that A must be at the start of the string. So the A plus in the parentheses states a grouping of A, and the plus states that the literal character A can show up one or more times. So it must show up once, and it can show up any more than once, but it needs to be in the string and at the beginning of the string. And then B matches the B character literally, and then the $ asserts that B must be at the end of the string. And then here are some regular expression methods that we will need to know. So search returns a match object, and matches can start anywhere on the text. Find all returns a list of strings or tuples of strings. Find iter returns an iterable of information returned by find all. Split returns a list of strings. So here are a couple examples of split. So we have I plus, and it returns the list of strings separated by i's. So you can have more than one I, and it'll separate them out. So you have A, B, C, D, and E. But note if we have I plus in a group, that it includes I in that list of strings. Next we have sub, which returns a string and replaces a pattern with the desired text. So here we have the grouping of A, and A can show up as many times as it wants, and it will replace groups of A with as. And then in the second sub example, you see that it takes the A's that are there, the existing group, and just puts parentheses around them, so it kind of makes them stand out a little more. So sub n does the same thing as sub, but it returns the information in a tuple format. I highly recommend you go into Python and kind of mess around with these methods and kind of see what they do, test them out with different arguments and parameters, different strings, and then different patterns, just to kind of play around and really get an understanding of what everything does. Continuing on with regular expressions, we have the extracting of groups for matching. Match objects record information about which parts of a pattern match a text, and groups are numbered in order of opening parentheses. So here are two examples. As you see in column 1, we have A as its own group, and then we have B as its own group, C as a third group, and then D as a fourth group. So notice how it's ordered from left to right, opening parentheses. And then if you see in the second column, A, C, and D all have a group, but B is not in a group. Now, why is that? Well, we can see that if it looks like this, where it has a question mark and then a colon, it's not an expression, and therefore it does not warrant its own group. So week 3, we mostly went over classes and operator overloading. So when we define a class, we are building the class name to an object representing the entire class. Now here is an example of constructing a class object. We have a class C, and then here's the init method with the value m and it having the value of the string starting. So if we set D equal to C, that means C and D share the same class object. When we set X to C with parentheses following it, this is actually constructing an instance of this class. And then when we set Y equal to D with the parentheses following, it's the exact same thing as calling it with C and the parentheses following. All objects have namespaces, which are dictionaries in which names defined are bound to or associated with values. So here are some crude ways of adding names to a namespace. So we're making a value C equal to this class C that we have. And so if you go ahead and print the dictionary, you'll see that it'll just print out M starting. But if we assign the value CX to be 1, this adds X as a key to this dictionary with the value of 1. And then below, we are assigning it more directly with the key value Z, and it being the value of 3. So if we go ahead and print the dictionary one more time, you'll see that has been updated with the newly added keys and values. Something that's very important in classes is the init method. So the purpose of this method is to create all of the attribute names needed by object methods and initializes them appropriately. So if we access a non-existent attribute name, an attribute error is raised. And now we're going to talk about operator overloading. So I'm just going to show you an example of the vector class, and then we're going to go ahead and define our class. We're going to call class, and we're going to call it vector. And then we'll start off with writing the init, so underscore init, init underscore, and we're going to give it, you always give your init self, and Eclipse automatically does that for you, and then any number of arguments, so args. And in here, we're just going to do self.chords, and then we're going to set that equal to whatever args are given to us. So the next method that we're going to write is the length method. So we'll do underscore len underscore, and that's just going to take self as always, and then we're just going to return the length of self.chords. Then we're going to go ahead and override the bool function. So bool, and that's just going to take self, and we'll go ahead and return for all values where v equals 0 for v in self.chords. So this returns true if all the values in chords are 0, false otherwise. And then we have we're gonna overload the repr or the represent function. So we have def underscore repr underscore giving it self, and then we're gonna return what it would look like kind of how you would and then we're gonna return kind of what it looks like when you're defining the class. So we're gonna have vector with this, then we'll go ahead and create a pair of curly brackets, and then we're going to go ahead and end this, and then we're going to do dot format, and then we're going to go ahead and give it self.chords. And then the last one we'll be doing for this specific example is the overriding the string method. So if you do underscore string, give it self, we're just going to go ahead and return, and what we're going to do is the long way so you can kind of see. We're going to do open parentheses, and then we're going to plus a string that is the length of self. No, that's not necessary. Plus, and then we're going to end it with parentheses, and then we're going to add to the string another string of the list of self.chords. So pretty much what this is in parentheses it has the length, and then following that it will have the actual contents of chords displayed as a list. Alright, so now we're actually going to make some vector objects and kind of show you what I have coded in the console. So we'll go ahead and run this code real quick so you can kind of see what the output is. So the length is 6 for v, which is correct. 1, 2, 3, 4, 5, 6. Boolean is true, so v2, all the values are indeed 0. For a rep or vector, this is exactly what we want. And then for string on v2, you'll see that there are 4 values, and then these are the values given. In week 4, we mainly talked about iterators, so we're going to talk about how iterators work, general review, implementation with nested classes, and then generators and decorators. So how do iterators work? Well, for a class to be iterable, it must implement the iterator protocol. So the protocol here is the iter and the next methods. And we should also note that a protocol is a group of methods that work together to accomplish a goal. Included in this protocol is a stop iteration class, which is an exception raised by next to note that there are no more values to iterate over. Alright, so now we're going to write a class called countdown, which really reflects how range works. So we're going to define the class, so class countdown, and we're going to do def, and then we're going to go ahead and write the init which takes self and a variable called last. And then we'll set self.last equals to last. Now last is going to be an integer that doesn't change, but it signifies when to stop iteration. Alright, so that is definitely not what we want. Thanks for nothing, Eclipse. So go ahead and there we go. And we'll go ahead and remove this because that is not necessary. Alright. So we're going to write the iter class, and iter must return an object on which next can be called. So it's going to return self, which is an object of the countdown class, which defines next, and that means that next can be called on it. So we're going to go ahead and write iter, and it's going to take self only, and then self.n equals self.last, and then we're going to go ahead and just return self. So this establishes self.n, which is changed in our next method, and it kind of sets a marker so that we know when to stop. So we won't be changing self.last, but we will be changing self.in, which has the same value as of right now. So if we go ahead and write our next method, we'll go ahead and give it self only. So we're going to say if self.n is less than 0, we're going to go ahead and raise the stop iteration. So that means we've gotten to the end. We don't want to go any further. Else, we are going to create a new variable called answer. We're going to set that equal to self.n. Then from from self.n, we're going to go ahead and subtract 1. And then we're going to go ahead and return answer. So this is the full class, and this kind of just goes through breaking it into separate chunks and going down through the iterations. So we'll go ahead and make the countdown class. So we'll do cd equals countdown, and then we'll give it the number 10. And then we'll go ahead and iterate using this cd object that we just made. So for I and cd, then we're going to go ahead and print a string of I, and then we're going to go ahead and add a comma to this, and then we're going to go ahead and set the end equal to just a space. And then after this is done, we'll go ahead and print blast off in all caps, and then we'll add too many exclamation points. So when we go ahead and run this, it should be from 10 down to 0. And so it'll be 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, and then blast off. So we'll go ahead and run this code, and we'll see that is exactly what we get. Moving on to generators. Now, Python has a special kind of function called a generator or a coroutine, and generators can easily write iterators. Generators are defined almost exactly like functions. The difference is that inside a generator are yield statements, not return statements. Generators can be restarted and picked up where left off, and Python remembers this information for generators, unlike functions. When we call a function, parameters receive values from its arguments, its body executes, and it returns a value. Then after returning this value, it is done and forgets the state of all of its parameters. The difference with generators is that when we call them, it receives a value from its arguments and does not start by executing the body. Instead, the generator suspends. To execute the body, we use the next function to skip to the next value. And generally, we use for loops on generators. And each time next is called, the generator resumes from where it was suspended and goes to the next time it calls yield. And then when an object is yielded, the specific value is returned. I'll just show you a quick example of a generator, and then we'll go ahead and run some code to show you what it does. So we're going to go ahead and import is prime from predicate. So import. Let's do is prime. This is underscore prime to be exact. And then we'll go ahead and write the generator primes. So def primes, and then we'll set a max, which will be equal to none. And we'll set a base variable, so p, which is equal to 2. And then we'll say while max equals none, or while p is less than or equal to our max, we'll go ahead and say if it is prime, p, that is. We'll go ahead and let's add a colon there. We'll go ahead and yield, not print, since this is a generator. We'll go ahead and yield the value of p, and then afterwards we will do p plus equals 1. We'll go ahead and code up a for loop for I in, we'll do primes, and then we'll do primes from 1 to 100, and we'll print I and then end. And we'll set this equal to a space, let's say. So this will print out all the prime numbers from between 2, which is our base here, and then 100. If we had nothing, it would just infinitely print out values. So here you go. Here are all the primes from 2 to 100. And then if we go ahead and take this out, and then we'll go ahead and take this out so it doesn't freak out everything. You'll go ahead and see it's just going and going and going. And so now we're going to talk about generators and space efficiency. Generators embody a small amount of code and often don't store any large data structures. So when writing a generator, you don't really want to take all the values from an iterable and just pile it into a list. That really defeats the purpose. Generators store or produce one value at a time, unlike most comprehensions, which produce lists, sets, or dictionaries of values that must all be stored at the same time. When writing generators, always try to avoid storing a large number of values in a data structure. Note that in some applications, Python must look at all iterables before deciding what to yield. And then there's actually a way to generate reverse values without ever storing the iterable in a list. And I'll go ahead and show you an example of that so you can kind of wrap your heads around generators and how you go about this. And then another generator example that we will go through is reverse generators. So there's two different ways we can write this. So there's one version where we save time, but that is at the expense of a lot of memory. And then there's another one which saves a lot of memory or a lot of space, but that's at the expense of time. So we'll go ahead and write the save time version first. So we'll go def reversed, that's 9 anyway. How you, nope. There we go, reversed, and then we'll do save time, and then we'll go ahead and iterable this. What is this? None of this is right in any way. Okay, there we go. Nope. Okay, there we go. So we're save time. So L equals list, and we'll go ahead and give it iterable. So this is taking the iterable that we're giving to the function, and we're just storing it as a list. Now all those values are being stored in this list, and we're going to go ahead and iterate through all of them. So for I in the range, and we're going to do I range. So this will be inclusive. Then we'll do the length of L, and then we'll go ahead and subtract 1 from that. Then we'll do to 0. And then we'll go ahead and do -1. So that -1 at the end, that third argument, pretty much just means you're going to go through it reverse. And then we're going to go ahead and yield L I. So you're actually accessing that information in that list instead of just generating one value at a time from the iterable. So this is going to use quite a bit of memory if you have a large iterable, but if it's smaller, then it's not really a big deal. Now, if you want to save space instead of time, so we're expecting to be dealing with some pretty big data structures, we're going to go to reversed save space, and we're going to give it the same iterable. And then we'll do, so we'll have length equals 0. And then for I in iterable, we'll go ahead and add 1 to the length. So length will be plus equal 1. And this isn't actually storing it. It's just storing an integer that is the length of the iterable. And then we'll go ahead and do for C in range of length. So of however long this is. So we're going to find the value at the index, length minus C, by restarting the iterable, then skipping length minus C minus 1 values and yielding the next value. So I'll go ahead and show you that in code. So we'll have a temporary value which equals iter, and it'll be the iterable. So this isn't actually storing, it's just turning the iterable into or it's turning the iterable into an iterable, if that makes any sense. You're kind of just restoring it as a temp value. So for I in range, and then we'll do length minus C minus 1. And then we'll go ahead and call the next on temp while that is the case, and while we're in that range. And then we'll go ahead and yield the next value after that. We're not going to tilde it, we're going to yield it. Next temp. And so that is a little bit longer code, and it takes a little bit more time, but if you're dealing with large data structures, this is the way to deal with large data structures and saving memory. Continuing on, we have decorators. Now, decorators are generators that take iterables as an argument and extends the behavior of the latter function without explicitly modifying it. So I know that's kind of dense with computer science vocabulary. I'll just go ahead and show you 4 examples of different decorators. All right, so moving on to decorators, I will be coding up for you guys 4 different decorators. Okay, so the first decorator we're going to write is repeat. So we're going to go ahead and declare this repeat, and we're going to go ahead and give it an iterable. So the point of this function is that it repeatedly produces values from an iterable. So we'll go ahead and do while true, and this will have it just keep going forever. And then we can do for I in iterable. And then we'll go ahead and yield that I value. So after the generator is done and gets to the last value in the iterable, it goes to the end of the while loop, and it goes back to the beginning and starts it all over. So it just keeps on running this generator over and over. All right, the next generator we'll be writing is a unique generator, and this produces unique values. So it'll never show you the same value from an iterable twice. So def unique, let's see, QUE, and this will also take an iterable. And then we need a set of things that we've already iterated over. So iterated will equal set. And then for I in iterable. So this will go through all the values of the set, and then we want to check to see if it's in our iterated set. If it's not in there, we'll go ahead and add it and then yield that value. So if I not in iterated, we'll go ahead and iterated dot add. We'll go ahead and give it I, and then we'll yield I. So once we've added it to iterated, if we encounter this value again, it'll say that it is now an iterated, and it won't run this code, and it'll just move on to the next value in the iterable. Next, we'll be writing a filter function which takes an iterable and a function and only returns values that return true through this function. So we have def p filter, and then we'll give it an iterable, and then a function, we'll call it f. So then if p, and we go ahead and give it the I, if that is true, then we'll go ahead and yield the value of I. And then lastly, we are going to write an enumerate function. So this is how you write the actual Python built-in function enumerate. So we'll go def enumerate, and you give it an iterable and a counter, and we'll just go ahead and set this value default to 0. So for value in iterable, we'll go ahead and yield counter and then the value, and then we'll go ahead and add 1 to the counter. So for I in repeat, and then we'll go ahead and give it L, print I, and then we'll go ahead and run this code, and it will just print 1 through 9 forever and ever and ever, and it'll just keep on going. If we go ahead and change this to unique, and then we will only add a couple more values in here. We'll just at random. Okay, and then we'll go ahead and run this code again. You'll see that it only prints out each one once, only the unique values. Continuing on to p filter, so we'll give it change this to p filter. We'll give it L, and then we'll give it a lambda, x, and then x equals, let's say 7. So for any value that equals 7, it will return. And so it returns 2 7s because 7 pops up in here once and twice. And then finally, enumerate. We can go ahead and do this. So enumerate. And we'll give it L, and we'll give it, let's say we want to start off with line 1. And then we'll go ahead and just print I. So there we go. So 1, 2, 3, 4, 5, 6, 7. So there's 17 values, and this is the order of them, how they appear in the list. And that is the correct behavior that we want from all of these functions. Week 5, we mainly talked about recursion, so recursive programming for ints, strings, and lists, functional programming, and then the map, filter, reduce, and lambda integration with recursion. So recursion, as you all know, is a programming technique in which a call to a function results in another call to the same function. And there are two main types of recursion. We have direct recursion, which is a call to the function that occurs in the body of the function, and then we have indirect recursion, which is a call to another function that calls the original function. And so here is the general form of a directly recursive function. So we have a function that solves a problem. We have our base case, which is an if statement that takes the minimum case that the problem can be in and returns the solution to it without recursion. If you're not at that smallest minimal state, then you will go ahead and run the else, which will decompose the problem into one or more similar smaller subproblems. It'll then recursively call solve on each of the smaller subproblems, and then combine the return solutions to smaller subproblems into a solution that solves the original problem, and then goes ahead and returns the solution to the original problem. So here I'm going to give you some examples of simple recursion with factorial and power functions. And then factorial just takes an integer n. And then we'll start off with our base case. So if n equals 0, go ahead and return 1. If it does not equal 0, then we will go ahead and return the current value of n times the factorial, so any numbers that are less. So factorial, and then we'll do n minus 1. And so if we go ahead and print factorial factorial 5, this should return 120, which indeed it does. So before we wrote it iteratively, this time we're writing it recursively. Okay, and as you see here, here's an iterable version of the power function, so finding the nth power of some integer a. But I'm going to rewrite it with recursion to make it a little shorter, a little simpler, a little more advanced. So we're going to do def power recur. That's going to take a and n. And then we're going to do if n equals 0, then we're going to go ahead and return 1. Else, if it does not meet that base case requirement, we're going to go ahead and return a times power recur. So there's the recursive call, and then a, and then n minus 1. So if we go ahead and find, if we go ahead and find, go ahead and comment out this code right here. So if we go ahead and run this code, we'll find that we'll give it a number 5, and we'll find the square of it. So power recur 5 squared. So this should return 25, and which it does. Something that's very important with recursions that we'll need to know for the test is how to proof a recursion. What are the proof rules? So that there are 3 main proof rules that you need to know. 1, you need to prove that the base case problem is processed correctly. So your base case must be correct. It must return the correct value. 2, you must prove that each recursive call gets closer to the base case. And then 3, you must assume all recursive calls solve their smaller subproblems correctly. So for an example, we're going to prove that the factorial function that we just wrote is correct. So for this function, the base case is 0, and according to recursive mathematical definitions, the factorial of 0 is 1, and this function recognizes the argument of 0 and returns 1, so that is correct. Second, we have if n is a non-negative number that is not 0, then this function makes one recursive call, n minus 1, which is closer to 0 than n is, which is also correct. And then third, we are assuming that factorial n minus 1 computes n minus 1 correctly. So the function returns n times factorial n minus 1, which is equivalent to n times n minus 1 factorial, which according to the mathematical definition is the correct answer for n factorial. Continuing on with recursion, we have structural and tail recursion. A recursive function is tail recursive if the result of the function returned by a recursive call is exactly the value computed by the recursive call, not modified in any way. So again, this is a kind of complicated explanation, and I'll just go ahead and show you an example of structural recursion and then show you that same example but tail recursion. So we'll have def list sum, and this will take a list of integers. And then if L equals a empty list, we'll go ahead and return 0. So that's our base case. If that is not the case, then we'll go ahead and return L, the first value, plus L from the one after that to the end of the list. And we'll go ahead and make the recursive call on this value here. Alright, so this is just structural recursion because you're returning a recursive call. You're not returning a whole sum. So when we're trying to make a function tail recursive, we're going to add an accumulator, which is where you use a nested class to kind of accumulate all the values, and then you return a call to that class. So we'll go ahead and do that now. So we have def list sum tail. Go ahead and give it a list. And then we'll go ahead and make another function inside of it, which is sum tail. And then that will take, we'll just name them for now A1 and then ACC. And then in here it's going to be if A1 equals a blank list, which is our base case. You're going to go ahead and return ACC, which is essentially the accumulated values that we have, not ACC check. And we can get rid of this import. Else. So if it doesn't meet that base case requirement, we're going to go ahead and return sum tail A1 from 1 to the end. And then A1 0 plus ACC. So we're passing the accumulated value. So at the very end, we can just return that value all accumulated together, and then we're returning that in the big function. This is incorrectly typed. There we go. So then for the bigger function, we're just going to go ahead and return a call to sumTail. And then we're going to give it the list and the value of 0 because that's where it starts out. L, and when we run this code, you see that they both come out to 15. Alright, next we have functional programming. So functional programming is a style of programming that uses simplicity and the power of functions to accomplish programming tasks. In a purely functional solution to a problem, there will be no mutation to the data structures, but instead a new data structure is built and returned with the desired changes, and recursion is the main control structure. Functional languages easily support and frequently use the passing of functions as arguments to other functions, and generally these are characterized as using immutable objects, so strings, tuples, frozen sets, and there are no state changes as stated previously. So the first function we'll be talking about that kind of shows this functional way of programming is map and transform. So this takes a unary function and some iterable of values and produces an iterable of mapped or transformed values based on substituting each value with the result of calling the parameter function on that value. So we have this map example here, which takes this function lambda and applies it to every value from 0 to 5. So this returns the value of x squared for every value from 1 to 5, and as you can see, that has happened. And then we have another value that takes an x and a y and multiplies these values together. So when you have two values in the lambda, you're going to go ahead and supply two iterables. So here we have a, b, c, d, e, and then we have range from 1 to 6, which is 1 to 5. So you'll see that it's A times 1, which will just give you A, then B times 2, which is BB, then C times 3, which is CCC, and it continues down the way. Next, we have filter. Now, this takes a predicate and some iterable of values and produces an iterable with only those values for which the predicate returns true. So here's an example. We're giving it the isPrime predicate, and we're going to apply this to a list of values from 2 to 50. So the value of this function produces a list of primes from 2 to 50, inclusive of those values. Next is reduce or accumulate, and this takes a binary function and some iterable of values and produces a single value. Here we have reduce, and we're giving it this function that just adds x and y, and we're giving it the range 1 to 100. So this is just going to go ahead and add all the values from 1 to 100, inclusive of 1 and 100. Again, we have reduce, and we're giving it the max function, and we're giving it the iterable of this list with these values, and this will go ahead and return the max value in the given list. Alright, so week 6 we talked mostly about linked lists, binary trees, structured trees, and a little more about iterative and recursive functions regarding these two. So linked lists are the simplest kind of self-referential data structures, and the LN class serves as the basis for all of our linked list code in this class. So here is the code for the LN class. And then here is an example picture of a linked list. And then I'll go ahead and show you an example of some functions. So we're going to show you how to turn a list into a linked list, how to sum all the values of a linked list, and then how to append a value to a linked list. So I'm just going to write these recursively for the sake of time. But you can definitely write these iterably as well. It's just a lot easier and simpler to write them recursively. So the first one I'm going to show you is how to turn a list into a linked list. So we're going to go ahead and write that. So list to LL, and you go ahead and just give it a list value. So if your list is equal to an empty list, you're going to go ahead and return none. Otherwise, you're going to go ahead and return ln, the class that we declared above, of the first value in the list, and then list to ll, and then we'll go ahead and give it the rest of the list values. If I could type, let's see, and then we'll go ahead and write another function that sums all the values of a linked list. So we'll call this sum ll. We'll just give it a linked list. And so if ll is equivalent to none, go ahead and return 0. That is our base case. Otherwise, we are going to return ll.value. So that is in the actual class. That is the current value that the linked list is currently at. So we're going to turn that value plus sum underscore ll, and then we're going to give it ll.next. So that moves on to the next value in the linked list and continues adding on. And then finally we'll have def how to calculate the length of a linked list. So this will be len ll. And for our base case, it'll be if ll equals none, they'll go ahead and return 0. Otherwise, we are going to return 1 plus the length, the length for the rest. So ll.next. Now, trees are a more complex self-referential data structure, and the TN class serves as the basis for all of our tree structure code in this class, and I'll go ahead and put it on the screen. Binary tree, which has a structure and order property. So structure dictates whether a parent node has 1 or 2 child nodes, and I'll go ahead and show you an example of a binary tree. Going back to trees in general, there are two standard metrics for trees. So there's size, that counts the number of nodes in a tree, and then there's height, which is the number of steps needed to go from the root of a tree to the deepest leaf in the tree. And here's some code that calculates the size and height of a tree. Another special kind of tree is expression trees, which can also use binary trees to represent expressions. And this is kind of just an example to show you how you would break down an expression into tree form. Moving on to week 7, we talked about type versus ISINSTANCE, inheritance, locating attribute names in an inheritance hierarchy. I'm going to show you an example of default dictionary and how this kind of applies, and then handling exceptions in an inheritance hierarchy. So in the case of type versus ISINSTANCE, calling type on an object returns whether or not the object is an instance of the object constructed from the class, while calling ISINSTANCE returns whether or not the object is an instance of the object constructed from the class, any other derived classes, or an attribute in the class or derived classes. Then we have the issue of locating attribute names. So via the fundamental equation of object-oriented programming that we talked about earlier, Python determines how to locate attributes for objects by first trying to locate the attribute in the object itself. Then if this fails, locating the attribute in the class from which the object was constructed. Objects mostly store their own state attributes, while the classes they are constructed from mostly store their behavior attributes. So objects keep their own state but share the methods that operate on them. And then I'll go ahead and show you an example of this with dictionary and default dictionary and how inheritance plays a role here. Okay, so I'm going to show you how the default dictionary class is actually written in Python. So it actually is inheriting a lot of its features from the actual dictionary class. So if we see, we'll write default dictionary class, so class default dict, and we'll go ahead and give it dictionary here. So it can inherit from this class. And then we'll go ahead and write the init method. And we'll go ahead and give it self, and then default factory, which will have a basic value of none, and then initial dictionary, which will equal an empty list, and then kargs at the end. And then we'll set the dictionary dot init. So we have to make a call to the init of all the classes that we are inheriting from. So we're going to give this self and then initial dict, and then we'll go ahead and give it kargs as well. And then we'll go ahead and set self dot underscore default factory equal to default factory. So this is used in overridden methods, this line of code here. And then this line of code initializes the base class. Def underscore underscore missing underscore underscore. I'll give it self and key. And then, so we're going to have if self dot underscore default factory equals none. We're going to go ahead and raise a key error. And then to make it a more accurate key error, we'll go ahead and make it string and key, so that will be the error message. And then if it doesn't raise that error, then we'll go result equals self dot underscore default factory, and then we'll go ahead and make a call to this. So we're going to call it and give it no arguments. And then we're going to do self key. And we're going to set this equal to our results. And why? Why does this happen? Why do bad things happen to good people? So self key. and then we'll go ahead and return the results. So again, what this method does is when accessing a key in a dictionary, the inherited method getItem, which does that task for us, is called. If it finds a key that is not in the dictionary, it calls self.missing and returns the result of executing this method that we just wrote. And then for handling exceptions, I'm just going to show you an example with the privacy exception class. So now I'm going to show you an example of creating a custom error. So say you're making some program that deals with confidential data, and you're trying to access it, and you want to throw an error if someone tries to access this information. So we're going to write a class called privacy error, and it's going to be really, really, really short. All it's going to be is class privacy error, and it's going to inherit everything from exception. And then what we're going to do is we're just going to pass it. That's it. When we have something that goes wrong that we don't want to happen, we want to raise a privacy error explicitly so the user knows this is private information. You cannot do this. So it inherits all of its methods and everything from the exception class, so you don't really have to write any code. In week 8, we talked mostly about the analysis of algorithms, complexity classes, and big O notation, complexity classes for standard Python operations, the analysis of code, and then the empirical analysis as well. So algorithm analysis is a mathematical area of computer science where we analyze the resources used by algorithms to solve a problem. The main tool for the analysis of algorithms is big O notation, which means growth in the order of. So oftentimes when talking about big O notation, the problem size is the number of values being processed. So this could be values in a list, a file, or other value like the number of digits in an integer. And then typically when we deal with big O notation, we want to look at the worst case behavior of the algorithm. So for example, in the max function, the worst case behavior executes 14n plus 9 instructions. So this means each time the max function loops, it runs 14 instructions, and then it also executes 9 instructions just once. And then here's a chart kind of diving deeper into big O notation behind this specific algorithm and this function. Another important thing to talk about when taking into consideration big O notation is the doubling signature, which is the time it takes to solve a problem twice as big as n. And here is a table of doubling signatures for some common big O notations. And then here is a chart of the big O notation for common Python operations. On the topic of analysis of code, we're going to focus on the code itself and determining the complexity. So the first important part in this is the law of addition for big O notation. So as you see here, O of f of n plus O of g of n is the same as O of f of n plus g of n. And then if we actually plug in some noticeable big O notations, you see O of n plus O of n log n is similar to O of n plus n log n. And of course, this simplifies to just O n log n, since n log n grows a little bit faster than just n. And here's an example. So our if statement, the complexity is O of n, and then our block 1 complexity is O of n squared. And then if it doesn't do either of those, it'll go into the else, and then the body of the else, the complexity is O of n. So to determine the complexity of this block of code, you'll do O of n plus the max of O of n plus O of n squared, which simplifies to O of n plus O of n squared, which finally simplifies down to O of n squared. Next, we have the law of multiplication twice. I'm just going to leave that in there. I don't even care. So we have O of f of n times O of g of n, which is equivalent to O of f of n times g of n. And so here's an example. We have our for loop statement, and the complexity of this is O of n. And then we have a function that runs every time this for loop is called, and the complexity of this is O of n squared. So to find the complexity of all this code, it'll be O of n times O of n squared, which is equivalent to O of n cubed. Moving on to empirical analysis, we're going to focus on timing and complexity. So we can use knowledge of the complexity class of an algorithm to predict its actual running time on a computer as a function of n. So here's an example. The complexity class for O of n squared is TAN, which is equivalent to CN squared for some constant C. Now, the constant C represents the technology used in calculating the outcome. So this kind of determines the speed that your specific machine runs the code. So let's say n is 10,000, and it takes 4 seconds to run some sort of code that has this complexity class, right? TA of n is equivalent to CN squared, and so TA of 10,000 is equal to 4, which is equivalent to C times 10,000 squared. And after doing some math, you'll figure out that C is equivalent to 4 times 10 to the negative 8th. By measuring the runtime of this code, we can determine the constant C, and we can estimate the time it takes for this specific complexity class to run on this machinery for any value of n. And then finally, we've made it. Week 9. And we finally made it to week 9, where we mostly talked about testing, Professor Pattis's performance class, and then unit tests. So testing is the process of running software and looking for errors actively and trying to make the program fail by testing a ton of different possible arguments. Once bugs are found, debugging begins. And it is very, very important. At a professional level, you want your bugs to be pointed out by a coworker or a friend rather than, having your boss pointed out or having a consumer pointed out. That is terrible. So it is always very, very, very important. I can't stress this enough to always test your code extensively. Back to the focus of the class, we have the performance class, which Pat has provided for us, and it's a tool that minimizes what we have to do to time code and gives us interesting information about the timing. Due to this video already being so long, I'm going to go ahead and link to the notes where this performance class is and let you guys kind of look through it and read through it. We also addressed this performance class in the last quiz that we did. So if you don't think you did too hot, Pattis should have released the answers by now, and you can go back and look at the answers and kind of just walk through the code and see what it does. And then finally, we have unit tests. So to test software, we must write both test and the software. So we're going to show you. So I'm going to show you an example of testing the sorting function. There are 2 specifications that a sorting function must pass. So one is permutation. So that means that the sorted list has the same values as the original list. And then 2, we have ordered. So that means that the values in the list appeared in non-decreasing order, which means that it is sorted from lowest to highest. And then the last example for this video, sorting testing. So I'm going to go and show you how unit test works. We're actually going to run some of Pattis's code that he has provided for us. So go ahead and get rid of that. We don't need it. There's nothing in that file. So if we go ahead, I will go ahead and explain this real quick. I'll run it. I'll change some information, and I'll show you kind of the errors that will occur. So we import random in unit test here, and then we have class sorting, and it's derived from unit test.test case. So we have our setup class, which is necessary, and we have a list that we have, which is just a basic. This is what it returns, and then this is what it should be after it's sorted. So 0, 1, 2, 3, 4, and then list.sort self.alist. So we're going to go ahead and call that to sort the list to see if the sort function works. Now here are our actual tests that are run. So our first function is test order, which just asserts that this call on alist returns a sorted list. So it calls self._isOrdered. So if we go down here to isOrder, it says for I in range of the length of this list, if the first value is greater than the second value, then we can return false, otherwise return true. And then next we have test permutation. So this checks to see if it's a permutation. So it's just going to assert that the count of self.alist is the same as self.sorted. If not, it'll go ahead and say that this list is not a permutation of the original. Values have been taken or added, and something here is not right. Bye-bye, My Chemical Romance. Okay, so we'll go ahead and run this code real quick. So you should get something like this. If you do not get something like this, you'll go ahead and just go run as, and then you should be able to run it as a Python unit test, and it'll check for permutations, and it'll say, okay, this is correct. It ran 2 tests in 0.001 seconds, and this is correct. So if we go ahead and change self.sorted and we go ahead and add a value, so we'll change that 4 to a 5, it'll go ahead and throw errors for both for just the permutation test, because when we change this 4 to a 5, it'll throw an error for just a pure permutation test, because it'll say the first has 1, second has 0. So that means this 4 was in the first one and this 5 was in the second one. So that's what's kind of throwing the error, and that's the what's wrong with the permutation. If we go ahead and change this back to a 4, okay, so if we go ahead and comment this out and then run the code, you'll see that it runs an error, and it says this assert statement here that this list is not in order. And if we look at it, since we're not sorting it, we're just getting 43120. I'm sorry, and that is definitely not the sorted version of the list. So what exactly is happening when we run a unit test on this code? Well, first we import the unit test module and then define the sorting class, which is a subclass of unit test case. The standard form of unit test usually has a setup method followed by a series of methods whose names start with test. Python then goes on to call unittest.main automatically, and this function finds every function in the class whose name starts with test and calls setup before calling each function. So in this specific class, it calls setup, then test ordered, then setup, then test permutation. So it resets the test variables for each function. And then if any test raises an unexpected exception, Python marks the test as failing and moves on to the next test.
Alright guys, so I really hope you enjoyed that video. Put a lot of work into this one. I've been working on it for over a week, a little bit every day, making sure I got it done before finals. If you have any questions, go ahead and leave them down in the comment section below, and I will try to help you out. I do tutoring for ICS 31, 32, and 33, so if you need any help, feel free to contact me. I have an email down below that you can email me at if you want to do some tutoring. Other than that, good luck on the final, everybody, and have a good day.